Let's start the video again. Okay, we are back, and to the final stretch of today's lecture, we're going to see a very important tool, which is the principal component analysis. So we're going to see principal components as descriptors, and we've seen that already today. We've seen principal components, and just fix that. Just a minute. So where have we seen this? We've seen it here, right? When we were talking about ellipses. We're talking about ellipses, right? Eigenvectors and eigenvalues. So this is the major axis, will be the first principal component of this data. The second, the minor axis, will be the second principal component of representing this data. Let's see then this analysis in more depth today. So we're going to see features as principal components. Basically, they are direction of the data that explain a maximum amount of variance. Maximum amount of variance. By capturing most important, by talking about direction, we're actually talking about lines that captures most information of the data. So what the principal component analysis does is it represents the data in a lower dimension. So you can do a lot more processing, a lot faster, in having more or less the same results in the end. We're going to see with a couple of examples today. These features for the principal component analysis are based on more than one image. So far we've seen features extracting from single images. Now we need features. These features are based on more than one image. So we're going to have a total. We need to assume that we have to start with a total of n registered images. So basically, as I said at the beginning of the lecture today, registered images images of the same object taken over and over again, whereby the object is every pixel in each image represents to this. Every pixel represents to the same object in every other image. That's basically this what I'm doing. So this is going to be this pixel here. So for instance. Let's see if that's the representation of my eye. This will be the pixel that belongs also to my eye region. That's going to be the same pixel belonging to my eye region. This from a number of pictures, so from n pixels. So basically, then what we are going to do is that the corresponding pixels at the same spatial location in all images are arranged as an n-dimensional vector. So these are all the pixels from the same location in the image, in the image, all registered. So these vectors can then be treated as random quantities. Each one of these vectors then will be a sample in my probabilistic distribution. So we can now talk about the mean vectors and covariance matrix. So the mean vector of the population always taking into account was a single pixel. So the mean vector is defined as by this formula. And then the covariance matrix of the population also has this formula. And this will be an n squared matrix, and this will be n times n matrix, where the main diagonal will represent the variance of the pixel, and the other pixels, the Cij pixels, positions in this covariance matrix will be the covariance between pixel xi and xj. Remembering that this is all a pool of values of the same pixel at the same location of registered images representing the same object. Okay. So following more on this idea that the corresponding pixels at the same spatial location in all images can be arranged as an n-dimensional vector. Then this notion has every pixel is now a point in a cloud. It's basically a population of pixels representing the same location in the image. So a set of images then is represented as a set of clouds of pixels, as a set of populations of pixels. That's quite a lot, right? So that's quite a lot. So if you imagine that we have n images, for every pixel now is not one pixel, is like a bunch of pixels representing the same thing. And if each image has a large amount of pixels, so we have a large amount of data. And we are dealing with this data as a probabilistic distribution over pixel values. So there should be a way to represent this better by using what we already know from linear algebra. Because in the end, we're all talking about a sequence of images of the same thing. So they are not images of different things, it's images of the same thing. So, and that's it. So what we want to get is exactly what we've seen in the ellipsis example. We want to get the main axis and the major axis and the minor axis, and the other not only these two, but all of the principal components of the data. If you are thinking about multiple dimensions, and we're talking about an n-dimensional space. In the ellipse, we're talking about 2 dimensions. So in an n-dimensional space, I'm going to have a whole bunch of important principal components. That's exactly the meaning of the principal components. What are the principal components of an ellipse? Is the major axis and the minor axis. What are the principal components of a cloud of pixels, for a set of clouds of pixels? These are going to be quite a few principal components, right? So, and what we're going to do is basically develop and try to understand what this whole field called, this tool is not a field, right? It's a tool called principal component analysis. This all starts from assuming the covariance matrix of the population. That this is the covariance matrix of the population. And there is a few mathematical notions that you can read in the book. And I think, honestly, I think the stuff in our book is not enough to understand this. There are other materials, and for those of you that are interested, I can point to a great book that develops this and a lot other of these methods into details, which is the Hastig statistical, I forgot the title, is statistical learning methods or statistical learning. It's free currently. It's free during this period via the Elsevier site. I'll make an announcement about it. So, but let's see it briefly. So, because this matrix is real and symmetric, finding a set of n orthonormal eigenvectors is always possible. There's a theorem about it. So let ei and lambda I be the eigenvectors and corresponding eigenvalues of this covariance matrix. And then we arrange that in descending order. So the first eigenvector and eigenvector is that with the largest eigenvalue, and so on. So let A be a matrix whose rows are formed by the eigenvectors of this covariance matrix of this whole population of pixels, arranged in descending order. Thus, the first row of A is the eigenvector corresponding to the largest eigenvalue, and the second row will be the eigenvector corresponding to the second largest eigenvalue, and so on and so forth. So this matrix of eigenvectors ordered in descending order according to its eigenvalues is used to define what we call a Hotelling transform, which is basically a matrix Y that maps your vector x's subtracted by the mean value of the population remember the X is a whole bunch of, it's actually this. So each X is a bunch of pixels representing the same location in a bunch of images. So we're going to do that for every pixel, for every X. And we're going to have a matrix Y subtracting X from the mean value of the population multiplied by this eigenvector matrix. Then, from the Hotelling transform and due to the properties of this matrix A, these vectors X can be reconstructed from I by just doing this simple algebra. Now, instead of using all of the eigenvectors of C, of the covariance matrix, we use only the k eigenvectors representing the k highest eigenvalues in a matrix AK. So this A is the whole, all of the eigenvectors. Imagine that we are in this n-dimensional space with multiple major axes representing the directions of representing most of the data. We don't need all of this. We just get the highest eigenvalues, and then we can then go back and get these y's that we calculated using this Hotelling transform. And we know we don't need to get the original data. We can reconstruct this data just using a handful of principal components. So this is a much simpler, lower dimensional representation of the original data, of the original images, but in a lower dimension. So this is so the principal components here are I'm only representing in image the principal components of the covariance matrix. Obviously, if I'm cutting a few of the components, a few of the eigenvectors and eigenvalues, this reconstruction won't be exact, but it will be good enough because I'm using the eigenvectors from that have the highest eigenvalues, right? So, well, basically, I've said that. So that's a pool of. If you imagine that as n-dimensional data, this is one principal component. That's the second principal component. And if you're thinking multiple dimensions, you may have other errors in other dimensions as well. And then I'm only getting the k, the k highest eigenvalues, the k eigenvectors with the k highest eigenvalues. So basically, what this method does, it's this stuff, right? So it's basically finding what are the directions of the highest variations in the data. That's a PCA for you. That's the principal component when it fits here. So it's going to fit in the principal components. An example of that. And so these are, remember from the first lecture that I gave, these are the multispectral images from satellite data of, I think, is Washington. This A is visible blue, B is visible green, C is visible red, D is near infrared, this is middle infrared, this is thermal band. So I can have multispectral from visual and from non-visual spectrum. Should have said non-visual spectrum, right? By using the principal component analysis, it gets the 6 principal component images obtained from vectors computed using this equation, right? So it uses the Hotelling transform. The Hotelling transform, then I get these vectors. After doing these vectors, I select the k eigenvectors with the highest eigenvalues. And then I get every image here that's been created using this transform here, and do the opposite conversion that's been done here. So from here, I got every point and get into a matrix. Now I get the matrix that I obtained by doing this kind of inverted Hotelling transform, and then get back to the original space, which is the space of the images. So I get back. So I get this pixel and fit it here, this pixel fit it there, but it's not, it's going to be not the original pixel, right? It's going to be the reconstructed pixel, the reconstructed matrix that has been reconstructed using only the principal components, which is a much lower dimension. So this is what we got at the end, right? So these are the 6 principal component images obtained from vectors computed using this equation. These are the values of the eigenvalues, right? These are the eigenvalues. Values of the eigenvalues is a funny term. These are the eigenvalues. This is the largest. Is represented here. The first has been used to reconstruct this image, and this is the second highest. This is the third highest, and so on. Right. So now, this is a representation, image representation of the eigenvectors. Now I can reconstruct it using the 2 principal component images corresponding to the 2 principal component vectors with the larger eigenvalues. So now I only get in these 2 eigenvectors, and now I'm not showing the principal components as I'm saying here. I'm reconstructing the whole thing. I'm reconstructing the whole image, and that's what I got as reconstruction. So this is the reconstruction of this. So you can see that it's pretty neat reconstruction, right? It's pretty neat reconstruction. I don't see much severe differences from this image to that, or from this to that, or from this to that. Somehow this image is not as good as this one. It has more or less the same features, but the intensities are different. And this is when you subtract, it's just to see the differences, you subtract the related images. So you subtract that from that, and the result is this. So you see that the first image is has not a lot of differences, whereas the last image has quite a lot of differences. So it's very different from the original, as we could perceive here. So this one is very different from that. Okay, and we can do that with much more complex data, and I've done that in the past. You can read in this paper where we used neural images from MRI data. These are the reconstructions using the 1, 2, 3, 4, 5, 6, 7. The 7 reconstructions of 3 models of mirror images from control is on the side, and schizophrenia group. These are not original images. These are reconstructed images using a number of the principal component analysis. And we use that to develop quite a few other things as well. And okay, so I think it's good for today. And I do recommend you to have a read. If you have, again, if you have 1 hour to dedicate to this topic this week, read this section on principal component analysis. This is, I can't stress more how important this method is. It's not only because it's applicable to images, but because it's applicable to the broader field of data analysis. And yeah, so happy dreams about happy dreams with PCA. I'll see you next week. So next week we are going to finish chapter 11. Just for scenes for the next chapters. Next week we're going to see the Harris-Stephen corner detection. That's the stuff that we ran on the practical last week. And we are going to see this in detail, and also a very nice algorithm, which is the scale invariant feature transform SIFT, which is a great algorithm. And maybe next week we are going to start talking about machine learning. Finally, we are getting close to the end. And that's it. Thanks very much, and I'll see you next week, hopefully. Bye.